Hi guys, welcome to Learn Electronics Repair. I have a subwoofer here, I guess from a home cinema sound system. This is a LG. Let's look at the model number. What do we have? Wireless active subwoofer S34A2-D. Okay, so this has a pairing button on it. I'm guessing it's either Wi-Fi or it's Bluetooth or whatever it is, but that isn't necessarily totally relevant because the fault is that it is dead. This was brought in by Handy Andy, who brings me quite a few things to repair. So let's see if I can get this working. You can see this is about 9 years old. Do we have the usual sort of problem with capacitors? Probably not, because at that era, really, the capacitor plague was no longer a thing. That was something that happened very much in the early 2000s. Let's have a look. Well, I guess the first thing to do is to plug this in. We'll connect it to the current limiter to see if it draws any power. Does any power go into it? And we can see if the light on the front comes on. So there, of course, you see the light bulb. I just need to switch this to limit. It's on direct main supply at the moment. So we're now connecting through the light bulb. We'll plug this in and switch it on. Now, because this maybe doesn't draw a lot of power, it's possible it will draw power, but the light bulb doesn't light. Let's have a look. Well, it lit up and went off, but the light on the front is not coming on. So some power's gone into here. That means probably this has a switch mode power supply, maybe. And if it does, then there may be large capacitors which are holding a dangerous voltage. So we need to be a little bit careful. I'll just switch that to direct mains and we can try again. No, it definitely doesn't light up. So let's have a look inside this and see if we can figure out what the problem is. I'm hoping that these screws around the edge are what's holding this in. There seems to be a few more, but they're probably mounting something to the back panel. No doubt we will find out shortly. It's possible this has a linear power supply, by the way. In which case it shouldn't be holding any particularly dangerous voltages. I don't think that's one of them. Looks like there's a PCB probably bolted here actually, which is what this is feeding into. There's a bit of weight in it, but it's not particularly heavy. So either it's not a very big amplifier and it's a linear transformer, or it is a switch mode. My guess, because of the way the light bulb came on very bright for an instance, it's probably a switch mode. Large power amplifiers, the very big ones, will do that with the linear supplies, but they have very large linear supplies in them, very big capacitors, and I would be surprised if this does. In fact, because there's no big heat sinks on it, it's probably a Class D amplifier as well. Let's have a look. So, yeah, it just lifts up. It is a switch mode power supply, I can see from here, with a large capacitor. So I'm going to be a little bit careful with this. This is the low voltage side. You can probably see if I show you down here. Okay. So this is the wires going to the speaker in the front panel. Although there isn't much of a front panel on this. Let's disconnect these. And out it comes. It looks like there's just two wires going down here, or the two cables. This, the heavy one, will be the speaker. This has 3 connections on it. I only see one LED on here. Maybe it's a bi-color LED. I can't think of any other reason why you would have 3 wires, to be honest. And there's no switches or anything down there for it to go to, that I can see anyway. Here is our amplifier. This is, yeah, some sort of Wi-Fi thing or something. Probably is like a Wi-Fi thing. I'm not too worried about it. And the power supply. So the first question is, does the power supply give any output? We know power gets into it because we saw the light bulb flash. I'm just looking now to see what voltages might be present. Nothing is marked, unfortunately. How about the other end? Little sticker here. Don't think anything's marked underneath that. So there's no marked voltages. I see two capacitors here. And what looks like, is this a voltage regulator? No, it's a diode. It has 2 pins on. Do I see another fairly large diode? Not really. So I'm thinking this quite possibly, from having the 2 capacitors, you think maybe it has 2 output voltages, but there's only 1 diode there, so you think it has 1 output rail. There may be another smaller diode somewhere. I don't really see it, if there is. Here is the opto isolator. So that's feedback, so the power supply can check the output voltage and increase the drive if the output voltage drops. On the high voltage side, this chip here with lots of legs on, that will be the switch mode pulse width modulator and MOSFET all in one, so that will be driving the primary of here. This is the input capacitor, the one that may have a high voltage in it, bridge rectifier, filters, fuse, and we can say for definite the fuse is okay because power got into it. This is the TL431, I would say that's the voltage reference. Let's have a look. In fact, you can see it says 431. It's not TL, it's SN, but it's just another equivalent of a 431. If we can get the camera to focus, you see it there. Okay, so that's what that is. This doesn't have any PFC or power factor correction. There would be another power device, basically, an inductor on the input and another large diode. So we can say for certain, because of the type of circuit this is, switch mode power supply, no PFC, that this capacitor will be connected across the output of this bridge rectifier. If it had PFC, that wouldn't be the case. There would be a diode in between. But because it is the case, what we can do is, quite easily, we can measure the voltage between the plus and minus on the bridge rectifier, and that will tell us if this has a charge in, a nasty voltage. Let's have a look. Okay, so I can easily get to the positive output of the bridge rectifier. I can just as easily get to the negative output. And it has about 39 volts in it, and that's been off for some time, 7 or 8 minutes while we were recording. So this was holding a high voltage and now it's draining away. That suggests strongly to me that the power supply is not starting. If it was starting, it had some load, this would discharge much faster. Okay. The same would apply if we had a short on the output, that would discharge much faster. Let's see. We can see something, it's here. This is telling us what voltages come out of this. It's upside down, but we can read it anyway, so we can see there is one output voltage, PVDD, on pins 6, 7 and 8. 9 has no connection. 10, P control. This looks like this switch is, I mean, it looks like power supply control to me, that P control on pin 10, which is this red one. I don't totally understand that, because you would think if there's some sort of control, that means that the logic board, this one, can switch this power supply on with a signal on the red wire, but to do that it would have some sort of standby supply. and I only see one voltage output. It tells us PVDD. Whether they do something very clever, which is to have the power supply coming up with a low output voltage initially, supplying this board, which then can send the signal back P control and switch it to the high voltage, I don't know. Let's have a look. So we want to see, do we have anything on the output pins 6, 7, 8, which are easy to get to? 1, 2, 3, 4, no connection. 6, 7, 8, so any of these will be the output. Any of these will be ground. Let's have a look to see what's coming out of our power supply. Well, nothing comes out of our power supply. There's no voltage there. So this can't possibly send the signal back P control because there's nothing coming out of it anyway. Switch it off again. And now I think we'll find out a very high voltage across the bridge rectifier. Dangerously high. Okay. Yeah, there, 285 volts. So that really does tell me that this is not starting up. That pretty much tells me that unless there is a short on the output, which we'll check now, then the problem is on the startup, it's this side of it. Let's have a quick look for short. So we'll go to the output, ground, any of these, out. And there's no short circuit there, okay? It's a high resistance, so we don't have a short holding this down, stopping it from starting. So it's probable that we have some fault on this side of it that's stopping the thing from actually running. We'll wait for this to discharge, then we can take the board off, and we can look up the data sheet for this chip, this one, and that should tell us a lot about what's going on and what we need to test. While I'm just waiting for it to discharge, let's have a look to see if we can read the part number. Yes, we can. So it's a 3BR. Just trying to get a light where I can see it. 3BR0665. So let's have a look at the data sheet for that chip. And here is the data sheet to our chip BR0665. And if we look down here, you'll see, as we know, it is a current mode controller. It's a pulse width modulator with an integrated MOSFET, 650 volt MOSFET. Okay, there's a picture of it showing the pins. And here is a typical application. So we can see our chip has a connection to ground. That's hot ground. That's this end of this large capacitor, okay? It has a supply voltage coming in, VCC. This is the bridge rectifier, so this is your AC main supply, which charges this capacitor. And this capacitor is the one that has the rather nasty high voltage in it on our circuit. And it retains that voltage because nothing's drawing power from it, really, or very little. That voltage, if you look, 320 volts, we measured it, goes to one end of the primary winding. So this is your switch mode transformer, and this is the primary winding, okay? The other end of the primary winding goes to the drain of the MOSFET inside the controller chip, the 0665. The other end of that actually comes out and says CS, this is the source, but also CS, which is current sense, and it goes through a resistor to ground, which is the ground here, hot ground. This sense resistor will be a low value, probably less than 1 ohm. And basically, as the pulse width modulator, the controller built in here, drives the gate on the MOSFET with on-off pulses, it draws pulses of power down through the primary, and the current that's flowing through the transformer flows through this resistor. So the chip is also monitoring the voltage here on the source of the MOSFET, and that's the overcurrent protection or short circuit output protection. Okay, so that is how the current limiter is working. It's inbuilt and it's monitoring this pin. Now on the transformer we have two other windings, two secondaries. This one is your output voltage. So this is your output voltage through a rectifier diode, in this case capacitor, inductor, capacitor. Ours I think just as a capacitor. And that generates your output, 12 volts, 24 volts, whatever it's using, 36 volts. And you can see here that that voltage is monitored by this circuit. This is your TL431, the voltage reference. And what this does, if you look, it connects to the cathode of the LED and the opto-isolator. The opto-isolator is also powered from here, and also the TL431 is powered from here. So basically, when the voltage on here reaches a certain level, which is dependent on the value of these two resistors, it will turn the LED on, and that signals via the opto-isolator on the feedback pin to this chip that it has enough output voltage. So this chip now can reduce the drive to the gate of the MOSFET, which reduces the width of the pulses coming down through the primary, therefore generates less output voltage, and when it drops too low, this will switch back off again. So that's how it knows to monitor the output voltage. That's the feedback, okay? Now you'll see there is another winding on here. Although it's drawn on this side of the transformer, this is a secondary. One end connects to hot ground and the other end through a rectifier diode charges this capacitor. And this supplies this chip with power, VCC. So effectively this chip generates its own power supply from another winding on the transformer. This is called the auxiliary winding, and that's how the chip gets its power. Now you'll probably think, chicken before the egg or egg before the chicken, because before this can generate its own power supply, it has to be switched on. This transformer has to be driven, it has to be running, but it can't be running if it hasn't got a power supply. Yeah, obvious. If we look then, when the power supply isn't running, we'll have 320 volts in this capacitor. As far as DC is concerned, this is just a piece of wire, so we will have 320 volts on the drain here of this MOSFET, because the power supply isn't running. This has got no power supply, no VCC. And you'll see internally we have this startup circuit, or startup cell as they call it, and that effectively is just a high value resistance that generates the VCC here. Okay, so when you first switch on via a high value resistance here, this chip gets power, VCC, and it can get started. It starts to run. The way it's designed is this resistor cannot provide enough power to keep this capacitor charged up. So once it starts running, the chip is drawing current and it starts to discharge the capacitor. And the idea is, before this discharges to the point where this stops running, it starts to generate its own power from here. It can only generate its own power from here if everything is basically working. For example, if there was a short circuit on the output, that would drag down the voltage in the secondaries. It wouldn't be able to develop enough power on VCC, so it would shut back down again. Quite often you'll hear power supplies where they go chip, 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 chip. What's happening there is basically the high value resistor, which can be external, starting the chip up. The chip drains the capacitor before it can start generating its own power, shuts back down again. The high value resistor charges the capacitor up again, it starts going again, and so on and so on. What we need to figure out then is why our chip isn't working. If we had a short circuit on the output, which we don't because we've measured it, this would be doing the chirp chirp thing, or at least it would be draining the large capacitor because it's trying to pull current through. Ours isn't starting. Most likely, either we have one of three things going on. One, there's no connection to ground for the chip. Two, the current sense resistor is open circuit, so it can't draw any power through here. Three, we have a faulty chip. We can't really have a lack of VCC startup because that's internal. If we do have, it's still a faulty chip. A faulty capacitor here would also stop it from working because it can't charge the capacitor up from the internal resistor, so it never gets a startup VCC. So I think we'll take this apart. We will check this resistor. We will check the connections to ground. We will check the connection from the capacitor through the primary to the drain pin. That circuit needs to be intact. And we will check this capacitor. While we're at it, we may as well check this diode as well. But from the way this is behaving, I honestly don't think it's even starting up at all. Otherwise, this would drain fairly quickly. Okay, so we have a plan. Let's have a look. While we've been looking at that, I expect this large capacitor is probably discharged now. Let's have a look. So from the positive to the negative of the bridge rectifier, 20 volts just over. So there is a little bit of voltage left in there, but it's not dangerous. So let's remove this board. Okay, here's a PCB then. We can just flick this over. We'll go to the large capacitor. We know it has a little bit of voltage left in it. 17 volts now. That's quite low, so I'm happy just to discharge that. Normally I would not discharge a large capacitor with just a screwdriver or something, but this has very little voltage left in it, so I really don't mind doing that. Saw a little bit of a spark there. That was fun, yeah. Don't do that on a fully charged capacitor, guys. It's bad for the capacitor, it's bad for the tools, yeah. So that is discharged. The reason I've discharged it is not that the 20 volts is dangerous, it's just it can mess up the meter readings. Okay, so when we're on ohms range, voltage present can cause all sorts of weird things to happen. Now let's have a look. So this is the positive end of the capacitor. The first thing I want to know is, do we have a path through the primary of the transformer to the controller chip? Okay. Well, the controller chip is here. You can see it's a rather strange layout. So we have like one pin there and one pin there, and then these like bunched together further back here. Okay. That has a resistor just fitted there, possibly an afterthought. So we can see marked drain, feedback, F, yeah, V for VCC. So we can pretty much see what they are without me even referring back to the data sheet. I'm guessing probably, where's the source? Well, the source will be whichever one connects via a low value resistor back to the negative end of here. We've seen that on the typical application. So let's have a look. So from here, negative end goes to one of the pins on here. I bet these are the low value current sense resistors. Again, I can't get a reading off it. It's very high. But I think these are the current sense resistors, but they're reading very high resistance, like the open circuit. Let's have a look. Well, I can see two resistors down here, and I think one of them's blown as well, just on the side of that capacitor. Let's have a look, see if we can see properly. Yeah, look at the coloured stripes, brown, brown, silver. Okay. So those are low value resistors. In fact, this second one's got a hole in it by the looks of it. Silver is a multiplier of times 0.01. Brown is a number 1. So 1, 1. If that was black, that would be 1, 1 with no zeros afterwards, or in other words, 11. If it was gold, it would be 1, 1 times 0.1, which is 1.1. In this case, it's 1, 1 times 0.01, which is 0.11 of an ohm, each 2 in parallel. So the total resistance is half of 0.11, 0.055, okay? That's very sensible for a current sense resistor. And that was an open circuit. We've measured them. They're open circuit. We can go again. That's where they are. R904, R905. Open circuit, okay? We also have a diode here. Let's just check that. So here's the diode. Do we see a diode junction here? Yes, we do. That's okay. And this is just a capacitor. So what's happened is the current sense resistors have gone open circuit. The question is, why would they do that? Well, why they would do that is if too much current has come down through here, through the resistor, or 2 of them in parallel in our case. And the only real reason that too much current would come down here is going to be that there's a short circuit on that MOSFET, or there's something wrong with this chip that's turned it on for too long. So let's have a look to see if we can find that. This time we're going to go from the positive end of this capacitor. We're going to check through the primary to make sure that isn't open circuit. We're going to find the drain pin, so we should have a connection from there to there, and we should not have a connection from there to CS. Just to make life a bit easier this time, I'm going to figure out where CS actually is, but really I don't need to, because it's on one end of these resistors, and it's on the end of these resistors which are not connected to the negative end of the capacitor. So let's not, because we don't need to look that up. Let's have a look at our PCB. Okay, so here is the positive end of the capacitor. This goes through a wire link here to here, and we can see that goes to one end of the primary. The other end of the primary will be here, because there's nothing connected there. It's here, and that comes down this way via another wire link to the drain. So that is the drain, and the source of this chip, in fact it's marked S here, goes to this end of these resistors, the other end of the capacitor. So if we go from here to here, do we have a short? No, we don't have a short. That surprises me a little bit. It actually reads open. I would have thought that would have read short. It doesn't. Is there any other reason why we might have a fault? Let's have a look. Well, we have here something called a snubber. This will be effectively a diode with the cathode to this end, so it effectively takes away the back EMF when this switches off. You get a very high voltage on this end of the coil. Will be a diode, probably connected through a resistor to here. It may just be the diode, or it may be a diode connected to a resistor and capacitor in parallel here. If that diode's gone short, well, that could possibly cause the problem as well. So let's have a look. Well, the diode in the snubber network is probably this. If you look down there, it says D901, so it is a diode, and we can check by where that's connected to. This is quite large for a snubber diode, normally smaller than that. So we know positive end of the capacitor comes into here. Other end of the primary, which goes to the drain, has a diode from there to there. Yes, and then look, a resistor and a capacitor in parallel back to the HT. That's exactly how I described it. So this resistor normally is quite a high value. Let's have a look. 55 kilo ohms, yeah, fairly high, not massively high. So we should be able to test the diode across here in diode mode. If the diode was directly across the winding, we couldn't, because it would just look like a short due to the winding, but because of that resistor, we probably can. And it's going to be in this polarity that it doesn't conduct. So this should not conduct. This end is normally positive and we don't want it conducting. We want it to conduct when this end becomes positive, the flyback voltage from the transformer. So this will read open and this should read like a diode. And it does. So the diode's okay. I don't see any short circuit across the drain and source of the chip. No, there's no short there. It could well be that this has failed and gone open circuit, that MOSFET, at the same time these resistors went open circuit. That's quite likely. So we're going to have to replace this chip and replace the two resistors, and then hopefully this will work. I'm not sure if I have these in stock. I'll have a look in a minute, but first of all, let's remove the components we want to just double check. I've switched on the vacuum desoldering device. This shouldn't be too difficult to remove. The only complication being that resistor between feedback and ground, I think is G. So let's just make a note. That's 104, which is 10 followed by 4 zeros. That's a 100 kilo ohm resistor. So if it does go AWOL during the desoldering, then we know what to put back in there. I'm not going to add any flux as it tends to block up the desoldering tool, but I will put some fresh solder on. I'm not going to worry too much about this resistor because I know what it is. I have them even if this one goes missing. I mean, I could unsolder it and put it on one side, but I have plenty of them. Let's see if we can actually do it as a challenge without desoldering that. Okay, so I think that's all of the pins, drain. Yeah, that's all of them. And these two resistors. I've noticed the desoldering gun has a tendency to clog up, so I've turned the temperature up to 399 from 380 because 399 sounds better than 400. And I think possibly now it won't have a clogging up problem. Let's try it. So wiggle it around a little bit. That's clean. I think that one's also clean. Let's see what we can do with this without removing the resistor, see if it's even possible. Well, one end's done. How about the other end? Yeah, I think I did it. How about that, guys? That was as much by luck as judgment, I think. Okay, we may as well do these resistors as well. Can't even show you how I'm doing this. Let's try. So desoldering tool on, waggle it around a little bit. Okay, one final clean and we're done with this. So 399 seems to be a nice temperature for this. Whether that will make the heating element last a bit less, I don't know, but we can buy them for about €13. So I'm not too worried. I'd rather have it not clogging up. Okay, let's see if our chip will come out. I haven't missed any pins, I don't think. Very difficult to get at. That's just typical. So I'll just try and actually just remove the heatsink with it. These are a bit large for using the desoldering gun, so I'm going to use braid. And this will work better with some flux. On the braid as well. Okay, let's try. I think I have that one. Other one. Yeah, maybe. It's looking mostly, maybe the other side I didn't quite get. Try. Let's see if we can remove this now. Well, it has glue on. Of course it has glue on, you know. Nothing's easy. What did we expect? Yeah, it's got glue on it. Ha, look at that. And it just fell out, yeah. Broke the glue, it fell out. So that's how to unsolder those, yeah, without removing the surface mount resistor. Okay, that's our chip. How about these two current sense resistors? They should just come out as well, I think. Let's have a look. Yep. And yeah. The chip, we probably can't really test that. There's probably nothing we can really do. Just replace it. It likely is faulty because I can't think of any other reason why the current sense resistors would go. Probably the MOSFET went short and the current that burnt out the resistors also then made the MOSFET go open. But these are easy to get. Let's look at these resistors. Well, this one now we can see clearly it's gone, it's blasted away the outer coating, so it was obviously a sudden burst of power that did that. This one was also gone, it's sort of in there where it's gone, you can see, but it has gone. And again there. So basically we need two resistors. These are 1 or maybe 2 watt resistors, I'm not sure exactly. I'd probably put 2 watt in if I have them. Let's see if I have one of these chips. I have to buy some parts for this. I don't have what I need. So this chip, the pulse width modulator with MOSFET, I can buy a pack of 5 of these for €3.80 plus a bit of postage. So it's about €5.50 for 5. That's what I will do. I can buy one for cheaper, but personally I'd rather just buy a pack of 5. If anything goes wrong, I have more for this, and they're useful to keep. If I find one faulty one, I'll probably find more faulty ones. So we can have that one. And there we go, guys. I think this one will work. If not, you will see it on a follow-up video. I'll initially try to get these parts actually from the Capital Las Palmas on Friday, which would be quicker. Otherwise, I will order from AliExpress. In fact, I may well order some anyway and just add them onto the bill. Then I have a few spare parts for future. I think this is a good example that goes to show that when you have a burnt out resistor, you should look for the cause of it. Okay, I couldn't find the cause of it, therefore I tested everything that was likely to be the problem. Everything seemed to test okay, so I suspect this chip being the most likely cause of these resistors to blow like this. I'm happy that the other parts, the bridge rectifier, the thermistor on the input, this one here that prevents the inrush current, and the capacitor, they must be okay because you're getting high voltage in the capacitor. So I don't think I really need to look at anything else on this at the moment. I expect you probably will not see it again because it will be working, but if it isn't, we'll have a part 2. Hope you enjoyed that. Maybe learned a few little tricks there, and I look forward to seeing you soon on another Already Electronics Repair video. Ciao for now, guys.